If you recognize the person in the photo from the thumbnail, that's actually related to our today's discussion. Today we continue discussing Riemannian metrics, Riemannian structure, and manifolds, and we would see, or we continue seeing, how that would define geometry on our manifold. Okay, so that's the main point of today's discussion. We would see some relation to a theorem of the person we saw in the thumbnail. Okay, let's get back to the basics. Let's remember in geometry, the two essential concepts are length and angle. Length of a segment or length of a vector or distance between 2 points, and angle between two vectors, right? Or two lines. Okay, we observed how length is defined using inner product. Also how angle is defined using inner product. So let's review that quick. We saw in Euclidean spaces Rn, or for simplicity, you can just think about R2. If you have a vector u, using inner product, we can define the length of that vector. So suppose some inner product is defined on Rn, it can be the standard inner product, or it can be some exotic one. We could define the length of u using inner product. That would be square root of u dot u, or inner product of u with itself. Also, if we have two vectors, u and a second vector v, let's say theta is the angle between them. The angle theta between u and v can be defined using this formula. Remember, we had the inner product of u and v is equal to the length of u, length of v, cosine of the angle between them. So if we have the notion of inner product, we can define the left-hand side. Using inner product, we can define the length of u and also length of v. So using this equation, we can see what should be the cosine of the angle between them. And actually, with a moment of thought, you can see from cosine of theta, you can see what theta is, say up to a 2 pi factor. So now we want to extend the same notion to smooth manifolds. We thought the essential thing to do is to define inner product on our manifold. Let's think about an example. Let's think about the two-sphere. Two-sphere as a smooth manifold can be realized as a Riemannian manifold in different ways. We can think about the standard two-sphere sitting inside R3 with radius 1, or the stretched one, right? This other one. As smooth manifolds, both of them are two-dimensional spheres. Although the other one doesn't look like a sphere, as a smooth manifold, they're the same. They're diffeomorphic. Right. So both of them are diffeomorphic to S2. But obviously they have different geometries. If I look at like curves or segments or kind of triangles and angles and lengths of things on one sphere or the other one, many properties are different. So they have different geometries. So if they're the same as a smooth manifold, what's the difference? The difference comes from having different Riemannian structure on them. Riemannian metrics on these two manifolds are different. So that's why the length and the angles and geometry on these two manifolds are different. They don't look the same, right? So usually we denote the Riemannian structure or Riemannian metric on a manifold with G. This is essentially the same as the inner product notion we had on Euclidean spaces. So let's say schematically this is our manifold. Let's denote it with M. Riemannian metric, let's recall that, means for any point P on the manifold, it's an inner product for vectors tangent to the manifold at a given point. So for any two vectors u and v tangent to the manifold at a point P, suppose we have defined what their inner product of is. Usually we denote that by g of u and v. Sometimes we use subscript p to say this is the inner product at the point P. Sometimes we use u dot v. They're all the same. Now, suppose it is defined at every point on the manifold, p, q, everywhere. That's what is called, that is the notion of Riemannian metric. And we would see how that defines the geometry of the manifold. So in fact, the different two spheres we saw, they have different Riemannian metrics. So suppose we have a manifold M, again, schematically, let's say this thing is our manifold. Let's say we have an inner product on the manifold. So it essentially means we have inner product on tangent space of the manifold. So there's an inner product on tangent space of M at P for every point P. This allows us to do geometry in the sense that it allows us to define length and angle, but for vectors tangent to the manifold. So say for any tangent vector u, we define the length of u to be the square root of inner product of u with itself, which we denote it as g of u and u. So if we don't have an inner product on a manifold, there is no notion of length. So there is no notion of length on an abstract two-sphere. We should fix the Riemannian metric on the two-sphere. Then with respect to that metric, we can say what is the length of this tangent vector. We can do the same, we can use kind of the same idea to use the angle between two vectors, tangent vectors u and v. So remember, we had this formula that the inner product of u and v equals length of u, length of v times cosine of the angle between them. We want this formula to be true, so we use it to define cosine of theta. So we have the inner product using that, the left-hand side, and the norms are defined. So this formula gives us what cosine of theta is. So here, inner product is kind of a more abstract notion than the one we had on standard one we had on Euclidean spaces. It's like a function which takes two tangent vectors and the output is a real number. So it takes u and v, so it's a map from tangent space of the manifold times tangent space to R. And by definition, it should satisfy three properties. It should be positive definite, which means inner product of any vector with itself should be non-negative, zero or positive, and it can be zero if and only if the vector itself is zero. So in other words, length of any non-zero vector must be positive. The second property is that it should be symmetric. Inner product of u and v should be the same as inner product of v and u, right? The inner product should not change. And finally, inner product should be linear in each component, or one should say it's bilinear. So if I pick three vectors u1, u2, v, and a real number c, inner product of u1 plus c, constant c times u2 and v should be inner product of u1 and v plus the constant c inner product of u2 and v. One should be able to expand this. Same thing holds for the second component. In fact, it follows from the symmetry, so I did not write that. Okay, so in order to do geometry on a manifold, just the manifold itself is not enough. We must have inner product. So the natural question to ask is that suppose a smooth manifold is given. Are we sure there is an inner product on the manifold? Can we be sure for any given manifold, one can define inner product on tangent space of the manifold? The answer is yes. So, in fact, there are many inner products on the manifold, assuming the dimension of the manifold is not zero. It's not just point or a couple of points. There are many inner products on the manifold. So theorem. For any given smooth manifold, there is a Riemannian metric or Riemannian structure on the manifold. So in the sense that for any given manifold, we can define inner product on tangent space of the manifold. So we can define inner product for tangent space at each point, and we can vary this smoothly. And as I said, there are many inner products, assuming the dimension of M is positive. It's not unique in any sense. So on any manifold, there are many different geometries, one might say. So we saw the standard two-sphere, but there was also the stretched one. But now you can think about a kind of stretch it and deform two-sphere inside R3 in a very weird way. That would give you another geometry on two-sphere, a non-standard geometry on the two-sphere. There are two ways to prove this. How can we see any smooth manifold has a Riemannian metric or many Riemannian metrics? One way is to use Whitney's embedding theorem. So we discussed Whitney's embedding theorem earlier in this course. That's one way to prove this theorem. That's actually how I'm going to do it now. There's a second way. It's very closely related to the first one, not really different, using partition of unity. Remember, in order to prove Whitney's embedding theorem, you should also use partition of unity. If you don't know Whitney's embedding theorem, the second way is kind of more concise and more brief. I'm going to do this using Whitney's embedding theorem. Okay, so what is the proof? Why there is an inner product on every smooth manifold? So the way to think about it is this. Whitney's embedding theorem says any smooth manifold, compact or non-compact, can be embedded inside some Euclidean space. So if I have a manifold M, let's say of dimension M, it can be embedded inside, you can think about it as a smooth submanifold of some Euclidean space of dimension 2m or 2m plus 1, any dimension. You can assume it's even higher dimension. It really doesn't matter. So there is a map iota which embed your manifold inside some Euclidean space. So think about the smooth manifold. It's an abstract manifold. There is no, it's like abstract two-sphere. It's neither the standard round one nor the stretched one. After embedding your manifold inside the Euclidean space, you can think about the two-sphere being, say, round or stretched. So think about your manifold being embedded inside some Euclidean space. Now it is a subset of some Euclidean space. It's not an abstract one anymore. This embedding allows us to define a Riemannian structure on the manifold. In fact, it defines an inner product on the manifold itself. Why is that? What is Riemannian metric? It means any point P I pick on the manifold, which now, because the manifold is inside R2m plus 1, this point is also inside R2m plus 1. I should look at the tangent space of the manifold. And the point is that tangent space to the manifold is also a subset of R2m plus 1 now, right? It's just a linear space sitting inside R2m plus 1. Pick two vectors u and v. Defining Riemannian structure on the manifold means I should say what is the inner product of these two vectors. But these two vectors are inside the tangent space at point P, but tangent space itself is inside R2m plus 1, right? So we must say what is G of U and V, what is the inner product of U and V. But because there are vectors inside Euclidean space, there is a preferred notion of inner product. Just look at their inner product as two vectors in R2m plus 1, right? R2m plus 1 itself has dot product. So just define that as the standard inner product of the Euclidean space. That gives you a real number. So when you have an embedding of your manifold inside some Euclidean space, that automatically and immediately defines inner product on tangent vectors on your manifold. Therefore, it defines inner product on the manifold. So note that, first, the embedding is not unique. There are many different ways to embed your manifold inside Euclidean space. So we embedded two-sphere in the standard one or stretched one. Every embedding defines a different metric. So for instance, when we embed S2 inside R3 in the standard round way, say with radius 1, that defines one metric on the manifold. And when we embed S2 inside R3 in a weird way, we stretch it, we twist it, that defines another metric on the manifold. Okay, so the induced metric on the manifold depends on which embedding we are picking. So if I pick a point P on S2, I can choose two tangent vectors u and v. So let's say u and v are two vectors tangent to S2 at the point P. Their image in the embedding, the first embedding, would look like two vectors. Their image in the second embedding would be two other vectors of R3. And their inner product, the angle between them, their length would be different. So different embeddings would give us different metric. You don't even need to embed S2 inside R3. You might embed S2 inside R4 or R5 or Rn for any n. And each embedding would give you a different metrics. So there are infinitely many embeddings, in fact, and therefore infinitely many metrics. So in some sense, the space of embeddings is infinite dimensional. So it makes sense to think about the space of metrics. Okay, so here we see one embedding We pick one embedding that gives us one metric. So there is at least one metric, but it's a good question to think about the space of all metrics, and therefore kind of the space of all geometries you have on a manifold. Okay. Okay. Now, again, let's say M is a smooth manifold. We know any manifold now can be equipped with a Riemannian metric. So let's say G is now a Riemannian metric on our manifold M. Again, schematically, this is our manifold M. Now I know for any vector u, tangent vector u, I can define length of the tangent vector. Great. But when we want to do geometry, we don't just want to be able to compute length of tangent vectors. We want to be able to compute length of curves. So let's say this red thing is a curve on the manifold. On the manifold goes from some point P to another point Q. So what is the length of this curve, right? That's another natural question one might ask in geometry. So let's denote the curve gamma. So the way to think about it is that gamma is a map from some interval inside R to our manifold, and we want to define the length of this curve. Let's go back to calculus. How would we define length of a curve inside Rn or even R2? Right, the simplest case. Let's say we are in R2. Let's say we have a curve in R2. So we think about it as a map from an interval AB inside R, say smooth move for simplicity to R2. Let's say this is the image of our curve. Let's say it goes from some point P. So at the time, we can think about the domain as time interval. At the time A, it's at the point P. And let's denote the variable time variable with t. At the final time b, it's at the point q. So what is the length of this curve? How did we define this in calculus? It's good to think about it for a moment. Okay, so the essential way to do this, again, comes from kind of inner product and knowing what the length of vectors. How can we define length of a vector? Think about gamma dot of t. This is derivative of gamma with respect to t. Thinking about gamma as a function or a map, we can take its derivative. At each point, it's a tangent vector to the curve. Do you see gamma dot being tangent vector? This is usually called velocity vector. It's a vector tangent to the curve. If we think about the particle moving fast, the length, the vector would be a larger one, etc. The length or norm of this vector is usually called speed, right? Now, the length of a curve gamma is defined to be integral of speed from time A to time B. So we integrate gamma dot of t dt, where t here is the dummy variable, going from A to B. Kind of makes sense. If you think about the kind of particle going with constant speed, that would be the simplest case. If it's constant speed, the norm of gamma dot would be a constant number. Let's denote that constant number with c. So it would be integral of c, and the integral of constant number is just c times b minus a, which is time interval. Constant speed times time interval should be the length of the curve, right? So it's kind of natural. Also, length is well defined. It doesn't matter how you parameterize it. If you go fast along the curve, if you go slowly, that integral would always give you the same number. Now we want to extend this notion with the same method to smooth manifolds. But the essential thing here is that we have a Riemannian metric on the manifold. This is necessary. Let's say gamma is a curve on the manifold, so it's a map from an interval a, b to m. Again, let's say it's smooth map. Let's say it goes from a point P, so gamma of A equals P, gamma of B equals Q. The time interval is AB. What is the length of the curve now? We want to follow the exact same strategy. This is kind of a definition slash theorem. So we do exactly the same thing. At each point t, look at gamma of t. It's a point on the curve and therefore on a manifold. Gamma dot of t, or d gamma dt, is the tangent vector to the curve. It's a vector tangent to the curve, therefore it's tangent to the manifold. Its norm, its length, the modulus, is called speed. Again, we integrate this number from a to b. This is called length, or defined as the length of the curve. The essential thing is that what is the norm of gamma dot? It is square root of inner product of gamma t and gamma t. So it's g of gamma t squared. Sorry, the square root is missing. So the length is only defined because we have inner product g, right? Because we have inner product g, we can define length of gamma dot. And therefore we can define length of the curve. Okay. So here, for simplicity, I'm assuming gamma is smooth. We can actually, it's better also to consider the curves which are not smooth, but piecewise smooth. So I'm kind of considering a larger class of curves. So what do I mean by piecewise smooth curve? So let's say schematically, this is our manifold. Rather than having a smooth curve, it can consist of some broken pieces. So let's say it's smooth from some point to another one, and then it's broken at just one point, and it's smooth from one point to another, and then there's a broken point. The point is that at those broken points, the derivative of curve is not defined, right? So one might say, what is gamma dot? It's not even defined. It's not differentiable. It doesn't matter. You see, the length of whole curve is equal to length of each part of it. And because each part is smooth, we can compute the length of first part, length of second part, length of third part, and look at their sum. The total number would be the length of the whole curve, although at those broken points, the integral is not defined. Just a few points does not affect the integral. Okay, great. So Riemannian metric, let's kind of recap. Riemannian metric allowed us to compute length of tangent vectors, right? Length of tangent vectors can be defined, tangent vectors on the manifold can be defined using Riemannian metric. So now we learned using that, we can define length of curves on the manifold. So if you have a curve on the manifold, we can compute its length. There is an extra step. Now we can define distance between points on the manifolds. This is actually why Riemannian metric is called metric. Usually in math, metric means you should be able to compute distance between points. So again, let's say schematically this is our manifold. Pick two arbitrary points, P and Q. A kind of natural question in math is that what is the distance between these 2 points, P and Q? Again, if you have a kind of you have an abstract manifold, there is no notion of distance. But if you have Riemannian metric, you can define this notion. Let's get back to Euclidean case. Let's say we have R2, 2 points P and Q. What is the distance between these 2 points, P and Q? So in order to define distance of P and Q, you can think about the vector connecting them, Q minus P, and compute the length of that vector, right? That would be the distance between these 2 points. The same idea does not exactly make sense over smooth manifolds. The essential thing is that first, subtracting points, P minus Q, is not defined when points are on manifolds. What is P minus Q? That really doesn't make sense. Plus, minus, these are defined for vectors. Manifolds are not vectors in general, right? If they're not flat, there is no, or just Euclidean spaces. So what does that mean? Even if you embed your manifold inside some Euclidean space, so now you have P minus Q. So think about two sphere, but with an embedding, you have P minus Q, but this is not what we really want as notion of distance, the length of connecting P to Q, because the vector connecting P to Q does not fall inside our manifold. I want to go from P to Q along the manifold, on the manifold. Look at the other red curve, not the direct one, but the one goes along the manifold. It's like on Earth, we don't define distance between 2 points as we go through the Earth. We think about it as going on the surface of the Earth. So for any 2 points, P and Q on a Riemannian manifold M, in order to define the distance between P and Q, we should look at ways we can go from P to Q on the manifold, but not inside Euclidean space, but on the manifold itself. So this red curve is one way, gamma is one way, let's say, to go from P to Q. Okay, so let's say gamma is a curve defined on some interval AB to our manifold. Let's say at the time, initial time A, it's at P, at the final time B, it's at the point Q. It's one way to go from P to Q. Let's say it's smooth or piecewise is smooth. It doesn't really matter. You can first go somewhere and then go to Q. You can have broken points like this other one. This is another way to go from P to Q. You go to one point and then you go to Q. There's a broken point there. So this is one way to go from P to Q. And then you can compute the length of this curve. So if you go from P to Q along that path, you have some length. But the point is that you want to look at all different ways you can go from P to Q and take the shortest one. That should be the path from P to Q intuitively. So you get infimo of this set. Loosely speaking, it's like taking minimum, but as I will explain for technical reasons, we define as infimo. It's like kind of like finding the shortest path from P to Q. Why is that? So consider the other blue curve. There might be a way to go from P to Q, but you go around and go somewhere else and go somewhere else and then finally go to Q. That's a bad way to go from P to Q. To compute distance, you want to find the fastest way to go from P to Q. So this defines a map from manifold times itself to R, or non-negative real numbers, to any 2 points P and Q. This function assigns distance of P and Q, which is a positive or non-negative number. This is usually in math, this is what is called metric. Distance is usually in math called metric. So the Riemannian metric was actually an inner product, but it defines a metric or distance function on the manifold. And just as a definition in math, we expect distance or metric to satisfy three properties. It's part of the definition. Distance should be non-negative. And in fact, distance, so it can't be negative, unlike Lorentzian or pseudo-Riemannian geometry. And distance can be zero if and only if the points are the same. So any two different points have non-zero positive distance. The other thing is that distance of P and Q should be equal to distance of Q and P. Actually, this might be weird if you compare it to everyday kind of experience. For instance, this shows modeling distance by time it takes to go from one point in a city to another point is not a good idea. Let's say this is map of a city. Let's say in this, there are like streets and blocks and buildings and roads. Let's say on this map, you pick 2 points, P and Q. The amount of time it takes to go from, if you want to define distance of P and Q, the amount of time it takes to go from P to Q in a city or length, it might not be a metric because some ways might be only one-sided. So going from P to Q, you might have to go along one route. For going Q to P, you might need to take another path. So the time or length in a city it might take to go from P to Q might not be equal to the time it takes to go from Q to P. So it shows that notion of distance is not really relevant to this one. Finally, we have triangle inequality. Remember, if you have a triangle with sides ABC, the sum of any two lengths of two sides, A plus B, should be larger or greater than or equal to C. Same thing should hold for any metric. If I pick 3 points on a manifold, PQT, distance from P and Q plus distance from Q to T should be at least equal to distance from P and T. So it's a good exercise to see that metric we defined using inner product and metric actually satisfies these three properties. So we started with metric, we define length of a vector. Using that, we define length of curves. Using that, we define distance between points on the manifold. So for any 2 points on the manifold now, we can define what is the distance between them. This is a well-defined function, can always be defined. It assigns a real number to a pair of points on the manifold. This does not agree with the distance, as I said, inside Euclidean space. So if I embed two spheres inside R3, 2 points inside R3 can be connected by straight line. That would be shorter than the distance defined on the manifold. Another related question. So I'm looking at all the ways to go from P to Q, compute the length of all of them, and take infimum on this set. The question is that, could I say, define the distance between P and Q to be the length of shortest path, shortest curve from P to Q? Do I need to define it as infimum of this set? Why didn't I say pick the shortest path from P to Q, define the distance between P and Q to be the length of this shortest path, right? The point is that this is sometimes not correct. Sometimes there is no shortest path. This might look a bit weird. So as an example, maybe think about this for a few seconds. What does it mean not to have the shortest path? So as an example, think about R2 minus the origin. Remove the origin from R2. This is our manifold now. Our manifold has a hole, R2 minus the origin. Okay. Let's say P and Q are 2 points. Let's say P is -1, 0, and Q is +1 and 0. I have 2 points. Let's say I want to compute the distance between 2 points, but as 2 points not inside R2, but inside R2 minus 0, minus origin. This is my new manifold. What is the distance between these 2 points? The point is that the distance is still 2. Think about curves going from P to Q, but they're inside the manifold M. Their length, as they get closer and closer to the x-axis, their lengths get closer and closer to 2. So the infimum is equal to 2. But there is no curve from P to Q with length exactly equal to 2. Because if you go directly from P to Q, you would pass through the origin, but origin is not part of the manifold. So this blue curve, which directly goes from P to Q, which kind of you want to say this is the shortest one, is not in the manifold. So there is no shortest curve in the manifold from P to Q. But still, the infimum of that set is equal to 2. The problem with this manifold is that it's not complete. It has holes. If your manifold is complete, we would see this in future lectures. If your manifold is complete, if it does not have holes like that, for any 2 points, there is a shortest path, shortest curve connecting them. There might be more than one, but there are shortest curves, and the distance would be the length of that. These would be actually examples of what is called geodesics. They are interesting submanifolds. We will study these. They're essentially quite important in geometry. So to wrap up and get back to the starting question about who was the person in the photo from the thumbnail, we learned every embedding of our manifold inside Euclidean space defines a metric on the manifold, and metric defines geometry. Right. Now let's ask the converse question. Let's say we have a smooth manifold M, and let's say a metric is given on the manifold, not via an embedding, just in an abstract way. Suppose I have a manifold with a Riemannian metric. In any way, I've defined inner product on tangent space of the manifold. Is there an embedding which that embedding gives exactly this fixed metric? So it's the converse question. First, I fix the metric, and then I ask, is there an embedding of manifold inside some Euclidean space such that this embedding would induce the exact metric I started with? So embedding gives metric is kind of the converse True, I'm not asking for uniqueness, but just one embedding which gives me this exact in this metric, right? The answer is yes. This is a kind of an interesting theorem. This is essentially proved by John Nash. Even if one is not a mathematician, one might have heard this name. Beautiful Mind is a movie about John Nash. We kind of discuss this theorem further in future lectures too. This is a kind of great theorem.